So greetings everyone. So in this episode, I'll be talking about waves generally. So this applies to all kinds of waves, whether they're water waves, light waves, sound waves, waves on a string, and so on. So these are some general fundamental concepts. So what is a wave? So a wave is a usually propagating oscillatory disturbance in a field or field. What does that mean? So let's unpack that statement. So a particle or an object like an eraser is described by lumped physical quantities. Things like the height of the eraser, the mass of the eraser, the volume, and so on. So for each object, you have a unique set of numbers. This is different from a wave. So take a look at this wave simulation. So watch this wave on a string. The first thing that you'll notice is that it's incredibly relaxing to watch this wave. Now, you can describe the wave by at least two parameters. One is the height of the string, and the other is how fast it's moving. So here's a drawing of the wave. So at every point, you have a different height, and also different sections of the string that are moving at different speeds, at different velocities. So here, height and velocity, these are physical quantities which are not lumped, like in the case of the mass of the eraser, but you have a different value at every location. Also is changing with time. So these kind of physical quantities, they're called fields. So they're varying with location and time. And so waves, you can think of waves as consisting of coupled fields. In this case, you have height and velocity. When you change the height, you have an unbalanced tension force that causes an acceleration, which leads to a velocity. So these two fields are coupled together. So other examples of waves are an electromagnetic wave. So X-rays, light, radio, and so on, these are examples of an electromagnetic wave. And these consist, as the name suggests, of electric and magnetic fields coupled together. You change one, that causes a change in the second, back and forth, and so on. In the case of sound, you have pressure and velocity. So when I'm speaking into this microphone, which is out of view over here, I'm causing the air to get compressed and decompressed, compressed and decompressed. At the same time, the air is moving back and forth. So you have these coupled fields of pressure and air velocity. I'm creating a little local breeze, so to speak. That's the sound wave. In the case of water, you have height, you have velocity, and so on. So generally speaking, the waves are consisting of coupled fields, and depending on the type of wave you have, you'll have a different selection of fields. Some waves can be described by lots of fields. For example, plasma waves, they have something like half a dozen fields. So as we continue to unpack this statement, we saw that waves consist of fields. Another keyword is oscillatory. What's that about? Let's take a look. Now here are a pair of sound waves. So one of them is at 80%. The other one, you'll notice the peak is slightly lower. It's 70%. But I'm going to play each of these in sequence, and let's play the two things added together. So first, the 80% that you already heard. Let's play it again. Now the lower one. So that should have been a little bit less loud. It's 70 versus 80%. Now let's play the combination of the two. You see, you added the two waves. You would expect that the sum should be more than either of them. It's actually less. So why is that? Let's take a look at the waveforms over here. So when this thing is going up, this thing is going down. So as a result, one is trying to increase the pressure, the other one is trying to reduce the pressure, and vice versa. When this is going up, here, this one is going down over here. So as a result, this is the point that the waves are oscillatory disturbances in a field. Not only are they disturbances in a field, they're oscillating, which means the field sometimes is positive, sometimes is negative. And this gives the possibility of cancellation. And that's what's happening over here. And this is the phenomenon of interference. So it's a hallmark property of waves that they can interfere because they're oscillating, sometimes positive, sometimes negative. So as a counter example, if you open a bag of potato chips, there'll be smell from that spreading throughout the room. That's never negative, it's only positive. So if you open a second bag of potato chips, the two smells will combine and they will add. They never subtract. So that's an example of a diffusive propagation of a field, as opposed to the oscillatory disturbance of the field that you have in the case of waves. And this now brings us to the last bit of unpacking of that initial statement. Once we've unpacked that, we can basically move into the new house and start living over there. Why do I have a usually propagating oscillatory disturbance in a field? Because in most cases, the waves you notice are traveling waves. So when I'm speaking, my sound waves, they're traveling. In principle, they could reach the other end of the earth. Similarly, when you look at waves on the ocean, water waves, they are propagating waves. But the situation where the wave could be confined, it leads to a standing wave. So here in the simulation, you have a string that's tied at two ends. It's tied over here and it's tied over there. This forces the motion of the two ends to be zero. You have what's called a node over there. So only the central portion go up and down. So the wave is not really traveling, it's a standing wave. Hence this qualification here, usually propagating. There is such a thing as a standing wave that does not propagate. And these standing waves are the basis of many musical instruments, and more on that later. But here's a little ukulele. So when I play this, I don't know if you can see the vibration of the string. Okay, so that's basically what's going on. The two ends, the string is tied over here, the string is tied over here, so the two ends are fixed, they kind of vibrate, you force a zero displacement. So you have motion back and forth, but the wave as a whole, the waveform does not move. So that's a standing wave. Now look at these two waves. The top wave, that's a wave on a string, and the one below that, that's a sound wave in air. So when I'm speaking, I'm causing the air to get compressed. It then gets decompressed because air flows. So you have a velocity field and you have the pressure field. Now the pressure is a scalar. There's no question of direction. But as far as the velocity field is concerned, notice that when the wave is going like this, the air is moving back and forth along it. So the vector is parallel to the direction of the motion. This is called a longitudinal wave. As opposed to that, look at the wave on the string above it. Why has that stopped moving? So look at this wave on top. The wave is moving this way. The height, the displacement vector, it is perpendicular to the direction in which the wave is moving. So a wave in which the field, first of all, it's a vector, and the direction of that vector is perpendicular to the direction in which the wave is moving, the propagation direction. This is called a transverse wave. So you have two common categories of waves, transverse and longitudinal. There are other types as well. And so here are those definitions for a transverse wave and for a longitudinal wave. Now, once you have a transverse wave, there's something else that go on with it. In the case of a transverse wave, as we saw, if the wave is moving in a certain direction, the field is perpendicular to it, but it can have different angles relative to the direction in which this thing is propagating. So look at the simulation over here. So right now this is said to be a horizontally polarized wave. The wave is moving this way and the wiggling of the field is in the horizontal plane. Let's see what happens when we rotate this. So this wave over here is polarized at 45 degrees. Let's change the angle further. Now it's polarized at 90 degrees. So this is the point. If you have a transverse wave, then you have polarization. This field is moving this way as it's going along. It has a choice of different planes in which to vibrate. That all of these planes are perpendicular to the direction in which the wave is propagating, but you can still have different angles, and that's the concept of polarization. So these are polarizing filters. They allow vibrations only in one plane to go through. So if you have two of these, if both have the same direction of polarization, light will go through. If I cross one of these, look at what happens. It gets darker, you see? So one is trying to let a horizontal wave go through, the other one a wave with vertical polarization. So when you have reflections off a road surface, especially a wet road surface, the light that gets reflected, it gets horizontally polarized. So by wearing glasses which have vertical polarization, you can cut down the glare. So that's an application of polarization. Now look at the string wave going across on the string. If I were to freeze the time, if I were to stop it, this is frozen motion. The thing you see is the profile of the wave at an instant in time. It's what's called a snapshot. So on the other hand, let's focus at one point on the string. Look at that little dot on the string that's in the middle. It's enclosed in a vertical rectangle. You'll see this thing is going up and down. It doesn't travel with the wave. So when a wave like this moves through, you don't have matter that's being transported. Everything goes up and down and goes back to its original equilibrium position. It's the shape of the wave that's basically moving. So look at the thing going up and down. We can make a graph of the height of that particle at different times in one location. That is called a waveform. So if you were to make a graph of that, that would be a waveform. If you were to freeze the time, then you have a graph of what the height is at different places at one instant in time. That's a snapshot. So you have these two concepts, the snapshot and the waveform. So let's look at these in more detail. So this is what those two corresponding graphs look like. So the top one over here, this is a snapshot. You're looking at the amplitude versus the distance over here. You're looking at the displacement versus distance. It's a string wave. The lower one here, this is looking at that particle in the middle, that rectangle which is going up and down. You're drawing a graph of its height at different times, but the location is one. This thing is called a waveform. That's called a snapshot. In the case of the snapshot, the distance between the two peaks, that is the distance, because this is the x that we're plotting. So that distance is called the wavelength, symbolized by the Greek symbol lambda. And for the lower one here, this is at one location. The x is not changing. The x-axis here, so-called x-axis, it's actually the time axis, the t-axis. So the distance between the peaks over here is not really a distance, it's a time, and that's called the period. And that's symbolized by capital T. Now the maximum height to which the displacement goes, that's called the amplitude. So it's going up and down in the case of a string. In the case of a sound wave in air is the pressure that's going up and down. Regardless, this question mark for the y-axis here, that's the wave variable, the field, whether it's the sound pressure, the height of the string, the height of a water wave, electric field, and so on. So you're plotting that field value as a function of space, as a function of distance, in the case of the profile, the snapshot, and you're plotting that field variable as a function of the time in the case of the waveform. So be clear about these two things, snapshot and waveform. So here's a summary of some of the important parameters for waves and their relationships. So first of all, you have the wavelength, the Greek symbol lambda, which is like an L basically. This is the wavelength, and this is the distance between consecutive points in the same phase. What do you mean by phase? If this were a plot of a sine function, then this would be the zero of the sine. The first peak would be 90 degrees. This negative slope going through the x-axis over here, that would be 180 degrees. 270 degrees, and so on. So 2 points in the same phase means two peaks, which are 290 degrees, 2 troughs, which would basically be 270 degrees, and so on. So 2 points in the same, 2 consecutive points in the same phase. That's what that means. And so that's the definition of wavelength. And the period t, that's the time between 2 consecutive points in the same phase. On a graph where you're plotting the waveform, the wave variable, the field versus the time, not the distance. So that could be 2 peaks, 2 troughs, it doesn't matter. That's the period. Then another definition, the frequency. As this thing is oscillating up and down in time, the lower graph here, the waveform, then the period is how long it takes for one oscillation. The frequency is how many oscillations you have per second. So it's the cycles per second. And that frequency is 1 over t, because let's say you have 5 oscillations every second. Each one, the period will be 1/5 of a second. So the frequency is 1 over t, and t is 1 over f. And then the speed of the wave. Lambda is the distance it travels in one oscillation. F is how many oscillations you have per second. So when you multiply the f and the lambda together, you get the distance traveled in 1 second. So that, of course, is the speed. Now, since f is 1 over t, as we saw right up over here, This can be written alternatively as lambda over t. So the distance in one oscillation divided by the time for oscillation. So distance over time is the speed. So this is the wave speed. So these are some of the important definitions and their interrelationships that you'll be using for all kinds of wave, whether it's sound, light, and so on. Now, when a wave comes to an interface with a different material, a different substance, then the three things can happen. One is it bounces off and gets reflected. That's the first case over here, it gets reflected. Secondly, it can go through. That's transmission. So that's this green one over here, number 2. It can get transmitted. The third thing that can happen is that it can get absorbed. So that second material just sucks up the energy, and part of the wave, part of the energy is essentially gone. So you have a combination of these three things. Now furthermore, as it gets transmitted through, it may bend, it may change the direction. So here the wave was going like this, and it got bent in a different direction. That is called refraction. So once it gets transmitted, may get refracted. So refraction refers to the bend. The direction of this thing gets bent. Now another point about reflections and transmission. When the wave crosses over into a medium where it slows down, it gets reflected upside down. The phase is inverted. If it goes into a medium where it speeds up, it gets reflected without an inversion. So look at the cases of these waves traveling on strings from left to right. So look at these two cases of waves on a string. In the first case, you have a thin string, and then a wave goes into a thicker string. In the case of a thicker string, that's going to slow the wave down. So when it reflects, it turns upside down. It gets inverted. In the second case, you have a thick string, then the wave transmits into a thin string. The wave is faster in the thinner string for reasons we'll see later. In any case, it gets transmitted without any change in the phase. But when it gets reflected also, there is no change in the phase. It remains upright, it's not inverted. So look at these two carefully. Yeah, look at the top one now. See, it came back upside down. Now look at the lower one. It's still right side up. The transmit is always right side up. So during reflections, you can have a phase inversion or not, depending on whether the speed is higher or lower in the second medium. And this will become relevant when you're studying interference in thin films. This brings us to the business of interference. We saw earlier, because the waves are oscillatory phenomena, sometimes positive and sometimes negative, they can cancel or add depending on the relative phase. So here's a sound file, a recording of a sound, where it's a normal phase. It looks like a sine. This is an upside down sine. It's 180 degrees inverted in phase. When you combine these things, you reduce the volume. You end up with less amplitude. And we saw a demonstration earlier. When you added the two things, you had less than both of them. On the other hand, if they're in phase, they will reinforce, and you'll have a higher volume, higher brightness of light. So this is the concept of interference. Now here, these wave files were artificially prepared to be upside down or non-inverted, but there's another way by which you can get a phase difference and hence a different interference condition. So what do I mean by that? Okay, now this may seem abstract, but I'll be doing a demonstration with sound shortly. Let's say you have two sources of light or two sources of sound, which are coherent. They begin in the same phase. They're phase locked. However, instead of being directly in front of this, let's say you're off to the side. Then what happens is the wave on this lower red path over here, it has to travel a longer distance. You have this extra distance. So there's a big D, the capital D, D2 and D1. These are the two paths that these waves take. The lower one has to travel an extra distance. That's this delta capital D, which is the difference between D1 and D2. Now, if the angle is theta, the off angle from the forward direction, then you can make a connection between this extra distance, the spacing between the sources, whether they're speakers producing sound or two slits producing bright light, and you can calculate this extra distance over here. So let's look at this. If this angle is theta, This angle in this little skinny triangle, that's also a theta. Now this spacing d, that's how far apart these sources are. So this is the right angle right over here. So as a result, this ends up being the opposite side. So therefore, it's equal to sine theta times this d over here. So that's the point. This extra delta d, which is the difference between d1 and d2, that's equal to the sine theta, d sine theta. So that's the point. This delta d, the difference in path length that you have over here, that's equal to little d, the spacing between the two things, times sine of theta. If that equals the whole number of wavelengths, the waves will be back in phase. If it's equal to a whole number plus an extra half wavelength, they will be out of phase. So what do I mean by that? So let me go back to my paper and pen. So here is what happens. These are the two sources of the waves. They're sending out waves to a point that's not right in front. It's off axis at an angle theta. So in that case, this path is shorter than this path over here. The d1 is longer than d2. d1 is more than d2. And here we have an angle such that you end up with an extra half wavelength, an extra half loop over here. So then when this is going up, this is going down, the waves are out of phase, and you will have cancellation in this case. So anytime this path difference is more than that by an extra half length, you'll have cancellation. If you have a whole number of wavelengths, they'll be back in phase. So you have an in phase, out of phase condition. You have when you have out of phase, you have cancellation. That's called destructive interference. When they're in phase, they add, you have constructive interference. And that's summarized over here. The delta d path difference, which is equal to d sine theta, the little d is the spacing. When that's equal to like 1 wavelength, 2 wavelengths, 3 wavelengths, so on, you have the constructive additive interference. When you have that path difference equal to m plus 1/2 lambda and extra half lambda, you have destructive interference. So this is a demonstration of the two-slit interference phenomena. You have coherent light going through these two slits over here. That projects an interference pattern on the screen over here. Let's change the spacing between the slits. So keep an eye on the slit spacing and see how this interference pattern on the screen changes. So this is the distance between the slits. If you bring the slits closer together, see? So as you bring the slits closer together, this interference pattern expands. Now let's keep this distance between the slits constant and change the wavelength. So right now we are at a green 550 millimeter wavelength. Let's increase the wavelength going towards the red. So you see, as you increase the wavelength, the interference pattern, it spreads out. Let's now reduce it towards the blue. So going from green towards the blue, notice that as I decrease this wavelength here, now I'm at 460 nanometers, the interference pattern shrinks over here. So later on, we'll get into the detailed math of this, but for exams like the MCAT, this is all you need to know. When you increase the wavelength, this thing spreads out more. When you reduce the distance between the slits, it spreads out more. So it seems counterintuitive, but it goes in the other direction. Okay, so I'm going to play a 2.5 kilohertz tone. This sound should be coming out through both of the speakers on your TV or laptop or whatever. Because of the interference pattern that we just saw at different angles, you have constructive, destructive interference and so on. As I play the tone, move your head around and see if you can catch minima and maxima. So here we go. So while that thing was playing, if you play it in stereo through two speakers, you should notice an interference pattern. So that's an example of interference using sound. The last bit of business as far as waves generally are concerned is diffraction. If you have a blockage over here, like a wall and some kind of an obstacle with an opening inside, if you have waves coming towards it, imagine this is like a wall and this is the sea, and that's the entrance to a marina or something like that. These waves, as they squeeze through that opening, they tend to spread out. They bend into a region which should be in a shadow. And this is diffraction, is the bending of waves around corners. And if the wavelength is longer and the opening is smaller, it gets spread out more. If the opening is relatively big compared to the wavelength, the spacing between these peaks over here, then most of it goes straightforwardly in the forward direction rather than bending out. So the diffraction effect is more if the wavelength is big relative to the slit or the obstacle that's in the way. And this is the business of diffraction. And here's a demonstration of it. So the microphone's in this direction, you can't actually see it, but let me hold an obstacle between me and the microphone. So this is blocking the line of sight to it. So here I am speaking, and you should still be able to hear me. There'll be some alteration in what goes through. So this ability to bend around obstacles is a characteristic of waves, and this thing is called diffraction. So here's a demonstration of single slit diffraction. So you have this laser light going through this single slit over here, and it casts a diffraction pattern on the screen back over here. So let's see what happens when you change certain variables. So the width of the slit, so this is diffraction. As the light is going through, it has to squeeze through the slit, and that causes it to spread out. So when you make the slit narrower, ironically, the light spreads out more. You'd expect you'll have a smaller bright spot on the bright area on the screen, but actually it spreads out more. So watch this. You see? So watch the slit over here is changing in width. So this is narrow, and slowly I'm making the slit wider. See? So the point is, as the slit gets wider, the diffraction pattern tightens up over here. As you make it narrow, you have a wider diffraction pattern. You have more spreading. Now let's keep the slit width fixed. Let's change the wavelength. So here I'm going to change the wavelength. So right now it's a green 550 nanometers. Let's make the wavelength bigger. See, as it goes towards the red, which is a longer wavelength, now it's 740 nanometers, you have a bigger spread on the screen. If I make the wavelength shorter towards the blue, the pattern gets tighter. So this is the point. It's a wave phenomenon, diffraction. And the longer the wavelength, the more it spreads out. And then you can also change the distance to the screen, and that's kind of obvious. If you move the screen farther away or closer, as you move it farther away, it's going to spread out more. And that's just because the distance from the slit to the screen has increased. So this is a quick demonstration of diffraction. We'll get into the equations later. For exams like the MCAT, this is all you need to understand, not the detailed math.